So we have discussed the concept of electrical equivalence in this class, right? I think we did it when we were learning how to combine resistors. And then we also did it when we were learning how to combine current and voltage sources. So there is an electrical equivalence between these two circuits, which is not remotely obvious. And so we are going to talk about the conditions that make these guys electrically equivalent. So on the left-hand side here, I have a voltage source in series with some resistance RS. And I'm going to call this a practical voltage source. On the right hand over here, I am drawing a current source, IS, in parallel with a resistor RS. And I am calling this guy a practical current source. So if I have these two circuits and I connect them to a load, and I'm going to call that load an arbitrary resistance, RL. What we will be discussing in class today, or at least for the first half of my lecture, is what makes these two practical sources electrically equivalent. And a large part of that is going to be causing the voltage drop over our load, VL, and the current source flowing through our load, IL, be identical, which is how we determined our electrical equivalence previously, right? We had a source and we said it was electric, we connected it to either a single resistor or a bunch of resistors in some potential configuration. And we said that those resistor networks are electrically equivalent if the same voltage drop appeared across the terminals of the network and the same current flowed into the network. We have the exact same situation here, but we're trying to make the source side of things electrically equivalent. All right. So I would like to talk to you for a moment about ideal and practical sources. All right. So if we have a simple independent voltage source like this, contributing some voltage Vs to a circuit, does it matter what I connect to that pair of open circuit terminals there? No. Arguably no, all right? Is there any resistance value that causes me a problem? So if I connect a resistor, some load resistance like so across it, and I measure some voltage VL across my load resistor and some current IL flowing through my load resistor, is there any value for RL that makes this break? Yes. All right. So knowing that the answer is yes, would anybody care to venture a guess as to what that value might be? There's two kind of obvious ones, right? At least I think they're obvious. 0 is one that could be potentially problematic, and infinity is the other one that's potentially problematic. So effectively, if I connect my voltage source to a short circuit, does stuff break? Absolutely. If I connect it to an open circuit, does stuff break? Not at all. So if RL is equal to 0 ohms, what does Ohm's law tell me that VL should be? 0 volts. But that short circuit is connected in parallel with a voltage source, having a voltage Vs, which isn't necessarily 0. So there's our problem, right? So another way to think about this is what's happening if VL is 0, our current IL is being forced to approach infinity amps. What does a current of infinity amps represent? An infinite amount of charge passing a point in our circuit in an infinitesimal amount of time. Exactly right. We have violated the laws of physics from the standpoint of our class if we connect a short circuit to a voltage source. Now let me ask you guys a question. If I take a battery out of one of these here multimeters and I apply a wire across both of the battery's terminals, do I rip a hole in the fabric of time and space? Not even a little bit, right? And so what this ideal voltage source neglects is the internal resistance of a battery or some other DC source, okay? We model that internal resistance. So we can model that internal resistance, practical. Voltage source here. So we model it by placing a resistance RS, so a source resistance in series with our ideal source. It is absolutely similar to that. Yeah, so typically speaking, the resistance of a voltage source is very, very small. In fact, the larger the resistance of a real voltage source is, the worse that thing behaves as a voltage source, because it is introduced, as that resistance RS gets larger, that means the voltage drop across that resistance RS also gets larger because of Ohm's law. So it's effectively taking away voltage from the source itself, right? Or it's lowering the amount of voltage that the source can supply. So yeah, so the closer it is to 0, the better the voltage, or the more ideally the voltage source behaves. So the internal resistance of, say, a standard 1.5 volt AA cell is on the order of 1/10 to maybe 0.05 to 0.1 ohms. It's not a very large quantity whatsoever. What that resistance does is it limits the amount of current that could be possibly supplied by that battery, right? And so what we wind up getting is a graph that looks like this for some kind of practical voltage source, all right? So here is our current, IL. Here is our voltage, VL, right? The maximum amount of current that can be supplied by this practical source happens when RL is equal to what? 0, all right? And so what would that maximum amount of current be if RL is equal to 0? VS over RS, okay? So on the left-hand side of this graph, we have what's called a short circuit current. ISC is equal to VS over RS. And on the right-hand side of the graph, what is the absolute minimum amount of current this circuit could provide? 0, which occurs for an RL value of what? Infinity. So if we connect this guy to an open circuit, then we have what's called our open circuit voltage, VOC. And what is our open circuit voltage going to be? So we are saying that RL is an open circuit in this case. So what does the open circuit voltage need to be? Just VS by itself. There can't be any voltage drop over that resistor RS if there's no current flowing through it. All right. And between these 2 points, we have what's called a load line. And goodness gracious. Okay. And this load line really just represents the ratio of current and voltage for any possible resistor value, all the way from 0 ohms to infinity ohms. So this characterizes the behavior of our source. And it's really just 2 quantities: short circuit current, open circuit voltage. Okay, those are the 2 parameters. They are related to each other by that resistance RS. That tells us everything we could possibly want to know about how any real battery behaves. My work outside of here, as I've mentioned a couple of times, is for Sabre Building Systems by Selections, where I make very, very large scale battery energy storage enclosures. I test those guys for short circuit fault conditions by literally using the open circuit voltage and the measured internal resistance of the battery, and then do all of my simulations based on those characteristics. In industry, that is what the 2 parameters for a battery are important. Short circuit current, open circuit voltage, internal resistance. That characterizes a battery. You don't need to know anything about how it's constructed or any of that. If you have those 3 parameters as an electrical engineer, you know every and anything you need to know about that battery. All right. Now let's take a look at ideal current sources. So if we have an ideal current source carrying some current IS, and we apply that current to some load resistance RL, measure our voltage VL, measure our current IL, are there any particularly bad values that RL can have in this case? So if RL is 0 ohms, any problems? No, our voltage VL would be 0. Our current IL would just be IS. Everything is pretty well behaved. But what if RL is an open circuit. We have an infinitely large voltage and no current flowing through our system, right? So if RL is equal to infinity, then we have IL is equal to 0 amps and VL is equal to infinity volts. So our problem here is twofold. IL of 0 amps is the current leaving our source, which isn't carrying 0 amps of current. So we have a kind of discontinuity there. And then when we have an infinite voltage created, that means that we are having an infinite transfer of energy for a finite amount of charge, right? Because voltage is work or energy per charge. So this is also a bad situation that we can't actually have happen. And so we correct for this by placing a resistance in parallel with our ideal current source. And what this resistance in parallel does is it limits the amount of voltage that can appear across the terminals of our practical current source. So in a physical sense, sure, practical. This one's actually probably a little bit harder to relate to a physical thing because a physical current source is not something that the overwhelming majority of us deal with. In truth, current sources are just transistor circuits where there is a relationship between the input voltage that you apply and the amount of current that you get out. So a true, anything approaching a true ideal independent current source really doesn't actually practically exist. But we can still logically work our way around to this problem, right? And so we are going to get a pretty similar graph. Relationship between our load current and our load voltage here. So when RL is equal to 0, what happens? What is the value for IL and what is the value for VL when RL is 0? VL is 0. Yeah. So our short circuit current is just IS, our voltage is 0. And then the opposite occurs. So when RL is infinitely large, our current obviously has to be, our load current obviously has to be 0. What is the value of the open circuit voltage then? Somebody who isn't Ian. I disagree. So if that resistor RL were taken out of the circuit entirely, right? So we replace it with an open circuit. What voltage drop occurs across the terminals? IS times RS, absolutely right. So our parameter is fully specified, or excuse me, our battery is fully specified, or current source in this case. Open circuit is IS times RS, and we have effectively an identical graph telling us how this guy behaves as our resistance varies from 0 ohms to infinity ohms. All right. So now now we come to the tricky part. Under what conditions are these two practical sources electrically equivalent? All right. So we have a practical voltage source. Connected in series with some resistance RS, or formed by an ideal voltage source in series with some resistance RS. And we want to know under what conditions yes. So under what conditions are these two electrically equivalent? And let's limit our scope to where RS on both sides represents the exact same numerical resistance. Okay. So for these two circuits, or portions of a circuit, if you will, to be electrically equivalent, regardless of whatever load is connected to them, let's look at a generic load impedance, RL, connected to both. All right. So if we have the same load resistance connected to both of them, I would argue that if IL is the same for both circuits, VL will have to be the same for both circuits as well, just due to Ohm's law. That's right. Our conditions for electrical equivalence are that VL and IL are identical. And if RL is the same in both circuits, if IL is identical, that satisfies both. All right. How could I express the current IL in my left-hand equation or left-hand circuit? So I would argue that RS and RL are in series. How do I express IL in my right-hand circuit? So I have a current source connected to two resistors in parallel, so I would argue current division is probably the easiest way to go about this, right? So if I use current division, I have IS times 1 over RL divided by 1 over RS plus 1 over RL. And this is mathematically identical to IS times RS over RS plus RL. You can easily prove that just by using simple algebra, multiply 1 over RS times RL over RL, multiply 1 over RL by RS over RS, and you get that result. So, under what conditions are these two things equal? Because we're no longer using the inverse relationship, so it's just algebra. RS is the resistor that we are not trying to find the current through. So this is literally why I didn't teach you this method of current division, to avoid this question, right? Algebraically, this is perfectly acceptable, and it's because the way that the math works out. So our current division is here. Our next step is just simple algebraic manipulation, okay? So I will prove it out to you just to make things a little bit, I guess, easier to swallow here. So I'm going to put 1 over RL here. And then I'm going to put, let's see, so this was 1 over RS multiplied by RL over RL plus 1 over RL multiplied by RS over RS. So what happens in my denominator here, I am going to have RL plus RS divided by RL multiplied by RS. And then up here, I just have 1 over RL, right? So I have a factor of 1 over RL in my numerator that I can get rid of. And I have a factor of 1 over L in my denominator that I can get rid of. And so I'm left with 1 over RL plus RS divided by RS. So when I take the reciprocal of that denominator, that's where RS over RS plus RL comes from, okay? So I do not expect you, nor do I want you, let me be very clear about this, to perform current division in this way that our second equation gets us. I am just trying to make an easy and obvious equivalence between the current IL on the left-hand side of the circuit, or the left-hand circuit, and the current IL on the right-hand circuit, because I need those two things to be identical in order for these two circuits to be electrically equivalent. So I ask again, under what condition are they electrically equivalent? Under what condition is IL on the left-hand side of the board equal to IL on the right-hand side of the board? All right. I have a common, our denominators are the same. What makes the numerators the same? When VS is equal to IS times RS. That's what I was going for with all this long-winded explanation. All right. So when VS is equal to IS times RS, these two circuits are electrically equivalent, which means we can convert any practical voltage source into a practical current source and any practical current source into a practical voltage source, which could potentially be used to simplify circuits, okay? So let me explain what I mean by that by a real jerk of an example here, okay? So let's say that I have the following circuit. And I was in a real salty mood. So I decided to give you something like this on your exam. So I'm looking at this circuit from the perspective of it being a potential exam problem. The reason why I include that caveat is because I know full and well that we could apply nodal analysis to this circuit or mesh analysis to the circuit. By the way, our goal is to figure out what this current I is. But I know that we could apply nodal analysis or mesh analysis to this circuit and figure out what I is. I don't want to say quickly or easily, but we could do it using nodal and mesh analysis. The problem is I count 1, 2, 3, 4, 5 meshes, which is one more than any of you with even the fanciest of calculators can solve on your exam. And I count 1, 2, 3, 4, 5 nodes, which means only those of you that have a Casio FX991 could do it. Anybody who had the 115 or the TI-36X would have to make some sort of simplification to work this problem on an exam. And if you just had a TI-30, you should go home and cry. Yeah. All right. But we can use this concept of source transformations to very rapidly bring this down to a level that we can easily solve. For this particular one, we could actually make this guy look like a single loop circuit that we could have solved on our second or third day of class in a few steps. All right. So how many practical voltage sources do I have in this circuit as it's drawn? Should be very easy to figure out. 0. If there aren't any voltage sources, there aren't any practical voltage sources either. Okay. So that's a pretty easy one. How many practical current sources are there? 3. There are 3 current sources in our circuit that are all in parallel with a resistance. Therefore, we have 3 practical current sources. So let's look at that 5 amp source in parallel with 3 ohms and what we can do with it. Okay. So what I'm going to do is I'm going to put a pair of terminals right here. This is me kind of subdividing the circuit up into manageable bits. All right. So if I have a 5 amp current source in parallel with a 3 ohm resistor, its electrical equivalent will be a voltage source in series with that same 3 ohms of resistance. Now I want to talk about the rules by which we apply source transformation. All right. So when we're converting from a practical current source to a practical voltage source, the tail of the arrow is our negative polarity sign, and the head of the arrow is a positive polarity sign. So if the arrow is pointing up, the positive polarity terminal should be on top. If the arrow is pointing to the right, the positive polarity terminal should be on the right. If the arrow is pointing down, the positive polarity terminal should be on bottom, et cetera, et cetera. Wherever the head is where the positive sign goes. Wherever the tail is where the negative sign goes. What value, what voltage value should this practical voltage source have in order to be electrically equivalent? 15 volts. How'd you get that? 5 amps times 3 ohms. Just good old Ohm's law, right? So what I'm going to do now is I'm going to erase everything to the left of those terminals that I drew. and literally disconnect that practical voltage source in its place. Because they are electrically equivalent, I can do that all day, every day, okay? So I erase that guy. I now have my 3 ohm resistor here. This is now a 15 volt source. And boom, I've done my source transformation. Okay. So think of it, until you get used to it, as literally disconnecting that part of the circuit, performing the transformation, and then plugging that part of the circuit back in. Okay. That'll keep you from making mistakes as to where the placement and all that kind of stuff goes. What did that source transformation do? It placed those 2 resistors in series. So they weren't in series before. There were no resistor combinations that we could have done prior to this. And now we can. And it also did something else. It eliminated a mesh, right? So that we now have 4 meshes. And I know you guys like mesh analysis, okay? So we now have 4 meshes. We could, just as was suggested, observe that the 3 ohm resistor and the 4 ohm resistor are now in series and combine them. And that combination there got rid of the node that we created. So we have 1, 2, 3, 4. We're back to 5 nodes, but we've eliminated a mesh. So in what other way could we simplify this guy? Do the exact same thing to the 1 amp source on the right-hand side of the network. The practical current source formed by the 1 amp and 9 ohm resistor. All right. So I'm going to draw my little terminals. Nine ohms. 1 amp. And I'm going to transform this into a resistor in series with a voltage source. So I have a quick question for you guys, kind of conceptual. Does it matter if I switch the order of the 9 ohm resistor and the voltage source up? So right now I have the 9 ohms resistor kind of on top, and then the voltage source, whatever it happens to be, we'll talk about that in just a second, over there on the right. Does it matter if I change their order? No, not even a little bit. I can change the order of the things in series all day long, makes no difference whatsoever. I can change the position of things in parallel all day long, makes no difference. Yeah. Yeah, so I could have, just as a, if this were back at 4, I could have put the 3 ohm resistor down here. That doesn't make the 3 ohm resistor and the 4 ohm resistor any less in series, because all 3 of those elements are in series. So I could still do that combination of 3 ohms in series with 4 ohms, looks like 7 ohms. It's less obvious. They're all carrying the same exact current, right? So if we were to apply Kirchhoff's current law, the current that leaves the 3 ohm resistor flows through the 15 volt source, and then it flows through the 4 ohm resistor. They're all carrying the same current. They have to be in series. There was no place for the current to branch off. Right? Anywho. what I'm getting at there, or what I'm trying to get at there, is that as long as the elements that you're putting back into the circuit are connected correctly. So if you're putting a practical voltage source in, you can put the resistor next to the other resistor or something like that to make those combinations more easy and obvious to see. Okay. So for example, well, it won't particularly matter, but anyway.
Would it be wrong if you were to put it like on the other side? Or does it make it easier?
So if I put the,
If you were to put 3 ohm on the bottom,
so if I put it down here, like I talked about a moment ago, yeah, there's nothing wrong about that, but it's not as obvious that you can combine that resistance with the 4 ohm resistor to give you the 7. So I'm saying this is another place where as long as you're doing everything appropriately, the order, you can change the order of your elements to make your connections easier to understand, right? All right, so we're converting that 9 ohm 1 amp practical source into a practical voltage source. So should the positive polarity terminal of my practical voltage source be on top or bottom? Top, all right. And what will the voltage be? 9 volts, easy peasy. So here's my 9 ohm resistor. Here's my 9 volt source. And we are now in 2 steps. Yes.
This may be a
I don't know that I understand your question. So for these transformations to occur, the source resistance of 9 ohms in this case for the current source has to be the source resistance for the practical voltage source as well.
oh.
If we don't have that resistor carry through, they can't be electrically equivalent because we're not forcing the same voltage drop to appear across the terminals and the same current to flow out of the terminals of our practical source.
Oh, we derive that relationship by keeping the source the same.
Exactly right.
I'm with you.
All right. So we now have this guy set up in such a way that we have 3 meshes. So we could stop here and solve it if we wanted to, but let's beat this horse straight to death. All right. We have one more practical current source, the 17 ohm resistor, in parallel with that 3Vx dependent source. So to make its terminals obvious, I'm going to erase these other sets of terminals here. We're not playing with them right now. What I'm going to do is I'm just going to scooch this 7 ohm resistor a little bit to the left. And say that I have a terminal here and I have a terminal here. Okay, all I'm doing is just trying to make it super duper obvious what I'm doing. All right. So my 7 ohm resistor, its overall position in the same circuit really hasn't changed because it's still between the exact same 2 nodes that it was. I just made it easier to draw a pair of terminals for me to unplug that practical current source that contains the dependent source, and then I can plug back in its equivalent. So we have between this terminal 17 ohm resistor in parallel with a current source direction to the right, having a voltage of 3Vx. So it is going to be electrically equivalent to a resistor in series with a current source between a similar pair of terminals, right? So this again goes to say, we don't really care if the resistor is on the left or the resistor is on the right. Whatever makes our future combination easier is what we should go with. So I'm going to go with this route here. So this is a 17 ohm resistor. I'm going to put my positive polarity terminal on the right because my arrow is pointed to the right. What should my voltage drop across this new dependent voltage source be? Yeah, just 17 times 3 times Vx, so 51 Vx. And so I can take this guy out. And I've made in 3 steps now that big ugly thing be a 2 ohm, or excuse me, a 2 mesh circuit, right? So we could still have to set up a system of equations. How could I force this thing down to a single loop circuit?
Isn't that a practical voltage source?
The voltage sources are in series, the two on the right. Can you combine a dependent and independent? So 9 plus 51 VX?
You could, but does that eliminate a mesh?
It certainly does not.
Yeah. So I have a practical voltage source on the left-hand side of the circuit now, right? I'm going to erase this terminal and erase this terminal. And I'm going to move this 7 ohm resistor, I guess maybe over here so it's a little easier to see. And converting that practical voltage source does is it now places that resistance, it'll place that 7 ohm resistance in parallel with that other 7 ohm resistor, allowing us to combine it. So just to be clear here, what I am suggesting, we have a 15 volt source in series with 7 ohms of resistance. So our transformation would be a 15/7 of an amp source in parallel with a 7 ohm resistor. That doesn't look enough like a 7 to satisfy me. 7 ohms. Yeah, so I moved it over so I'd have more space to put my terminals or whatever, yeah. But that 7 ohm resistor was still in between the exact same 2 nodes. So moving it didn't have any effect on the configuration of the circuit. So I do my source transformation. I have 15/7 of an amp in series, excuse me, in parallel with 7 ohms, in parallel with 7 ohms. And now I can combine those 7 ohm resistors to look like 7/2 of an ohm. Now I could do one more source transformation. So 15/7 times 7/2 is going to be 15/2 of a volt. Positive polarity on top. In series with 7/2 of an ohm. And I have a single loop circuit that we could have solved 3 weeks ago. Madison. Just to make that simplification. Now, I know, I'm fully aware that because we know nodal analysis and we know nodal analysis and we know mesh analysis, we could have just simplified it once or twice and gotten it into a state that we could have solved it based on our current amount of circuits knowledge. But it's a powerful enough tool that if the circuit is of the right form, we could actually make it to where a freshman engineering student could have solved this if they knew what the heck a dependent source was or something like that. Okay. All right, so are the rules for applying source transformation clear? Let's start there. Hopefully reasonably clear. If we have a voltage source in series, yes, ma'am. Sure. Whenever we have a voltage source connected directly in series with a resistor, we can convert it into a current source in parallel with a resistor and vice versa. And we can use that to simplify complex circuits into things that are a little bit more manageable. All right, so the next topic that I want to talk about builds off of this and has to deal with the concept of maximum power transfer. Justin.
What did you do after you made 15.7 amps and this parallel with 7 ohms?
I combined the 7 ohm resistors together to make a 3.5 ohm resistor. And then I did one last source transformation. So I'll write that one down. So what I had was 15/7 of an amp in parallel with 7/2 of an ohm. And I converted it to 15/2 of a volt in series. If I have two 7 ohm resistors in parallel, they make 7/2, 3.5. Right? If I have two identical resistors in parallel, the equivalent resistance is just half the resistor value. And that was the last simplification that I made to put this guy in it, make it look like a single loop circuit. All right. Let us now talk about maximum power transfer. So if we have a practical voltage source, I'm going to use a specific value for the voltage and a specific value for the resistance. Yeah, okay. And I wanted to determine what the power absorbed by that load resistance was. What might I do? Okay. So the power absorbed by the load resistance, PL, sorry, that's not a P. Is simply the current flowing through that load resistance squared multiplied by the load resistance itself, right? I squared times R is the power absorbed by a resistor. Everybody okay with that? Could also potentially do V squared over R, but that's not how I have it written in my notes. What is IL squared here? Or what is IL? How can we figure out what IL is for a given value of RL? We did this literally like 10 minutes ago.
And over 10 plus RL.
Exactly right. 10 volts over 10 ohms plus RL, quantity squared times RL. So generically, this would look like VS over RS plus RL, quantity squared times RL. All right. So if I plotted this equation, 10 over 10 plus RL, quantity squared, times RL, what it would look like is something like this. I'm going to try to draw it as uncrappily as possible. Yeah, so the blue is just if I didn't know that the voltage was 10 volts and the source resistance was 10 ohms. So I'm just putting it in a general case. So this is our power measured in watts as a function of load resistance measured in ohms. And it would look something like this. Where there is a very finite value of RL that corresponds to maximum power being transferred by this practical voltage source to its load. Another interesting thing to be, this is a roughly parabolic shape, which makes sense because we have 1 over R squared dependency on the bottom, right? So it's depending on the resistance squared on the bottom there. So if we, excuse me, it's why we have this parabolic shape. So we can see that they're like, if arbitrarily, if we wanted to design a circuit for a specific amount of power, and we didn't care if that was the maximum amount of power that could be delivered, we actually have 2 choices of resistors that we can go with. I am mentioning this to you because you have a homework problem set up in such a way, and if you do not notice and observe this parabolic relationship that I'm giving you right here, it will be an absolute nightmare to solve. But if you notice the equation that I'm pointing at directly on the board right now, it makes it much, much, much easier. We absolutely covered this. Okay, so I just want to be very, very clear about that. All right, so how would we go about determining what that maximum resistance is? Take the derivative and set to 0. Absolutely right. So let's look at this guy right here just in general. So we're going to wind up having VS squared times RL divided by RS plus RL quantity squared. This is our power that we're trying to maximize. So the suggestion is we take the derivative of this guy and set it equal to 0, right? So PL max can be determined by taking the derivative with respect to RL of VS squared multiplied by RL divided by RS squared plus twice RL plus RL squared. Setting it equal Excuse me, that's not the right one. You take the derivative. And set it equal to 0. I'm not going to force you to do this math. Okay, in this class, the only calculus we need to know how to do is differentiate and integrate sinusoids and exponentials. Everything else is hippie mathematician stuff. All right. Pardon? Sinusoids, so sines and cosines, and then exponential functions. I think you do. So the result that we get here is that maximum power transfer occurs when RL is exactly equal to RS. This should kind of intuitively make some sense. Maximum power transfer occurs when RL is equal to RS. So that is the result of us taking the derivative of this expression, setting it equal to 0. We find our RL value. From this, it should be pretty straightforward to see what our maximum power delivered by any practical source could be then, right? So P max would just be this guy right here evaluated where RL is exactly equal to RS. So what happens? Well, we're going to have VS squared times RS divided by RS plus RS quantity squared, sorry, which looks like, so it shouldn't be an equal sign. VS squared RS over, so twice RS squared is going to be 4 RS squared is simply VS squared over 4 RS. So if we ever want to know what the maximum power that can be delivered by a particular practical voltage source is, that's it. I know that this probably isn't that big of a deal to you guys right now, but the next topic that we are going to learn is called Thevenin and Norton equivalent circuits. And it is going to allow us to transform any two-terminal linear network into a practical voltage source or a practical current source, which means we can take any linear circuit, no matter how complex it is, break it down into 2 elements, a voltage source in series with a resistor or a current source in parallel with a resistor, and then use that equivalent to do all the power analysis that we could ever need. Very, very powerful thing, so that you don't have to attribute for everything. You know, it all behaves generally like this thing. So that's how I can determine whether or not, like what the power rating of my resistors need to be in my transistor circuit and all that kind of stuff, so that I'm not going to burn components out and all that kind of jazz. Very, very powerful tool. If we had a practical current source, just say we have IS in parallel with some resistance RS, parallel with some resistance RL. Here's VL, here's IL, our power. Still be IL squared times RL. So that's going to look like IS multiplied by 1 over RL divided by 1 over RL plus 1 over RS squared times RL. We would figure out the maximum power by maximizing that thing. Actually, I can make this as IS times RS over RS plus RL quantity squared times RL. And if we recognize that IS times RS is just the VS from our previous work, we should observe that we get the exact same results. Maximum power transfer occurs for a practical current source when RS is exactly equal to RL. And maximum power now will be 1/4 IS squared times RS. All right. So one last quick example problem. I do have an in-class assignment, but honestly, I mean, we can spend some time doing it, but I wouldn't mind if we knocked off a minute early. Whatever way works with you guys. So, sure, sorry. All right. So let's say that we have the following circuit. This is going to be kind of tying everything we've done today together. We have a 12-volt source in series with a 3 ohm resistor. Here we have a 6 ohm resistor, a 7 ohm resistor, and then some resistance RL. We want to know what value of RL will cause the remainder of the circuit to deliver maximum amount of power and what is the maximum amount of power that RL can absorb. So just as a heads up, on your exam on Monday night, this isn't the circuit, but this is literally how I will test your ability to handle this type of problem. Is I will give you a circuit that looks like this, roughly. First part will be what value of RL gives you the maximum, causes maximum power transfer to occur. Second part of the question will be, what is that maximum power? Okay. So our goal here is to make everything connected to the left of those terminals I've just drawn look like a practical voltage source or practical current source. Joy, what's up? Multiple choice. I usually put 10. 10. Well, one of them is none of the above answers are correct. So I guess Huh? So none of the above answers are correct is there for when I make a mistake. So like if you work it and you're 100% correct that your answer is right, or you 100% believe that your answer is right, you can't find a mistake or anything like that, and it's not showing up, there is a small but non-zero possibility that I made the test question at 3 o'clock in the morning and wasn't paying attention to crap. That is my save my ass answer. Generally speaking, what happens is if you guys can prove that the correct answer was not available, which is literally just, hey, Dr. Hartman, I don't think the correct answer was available. Would you mind looking into this? Or I will look at it when I do my statistical analysis to see what the correct response rate was for all the questions and if anything seemed low. And so by low, I mean less than 20%. So if less than 20% of the 100+ students who are attempting this test are able to answer the question correctly, that means one of two things. Either it wasn't covered well or the correct answer wasn't available. So I check to see, and if the correct answer was not available, everybody winds up getting credit for that. So you might get an extra point or something if you were able to successfully be like, I don't think the answer was here. I've seen the largest instance of that ever occurring is 2 questions on a 35 question test where I've made 2 dumb mistakes. Okay, so they don't happen a lot, but they do happen. So I put that answer on there to save my butt, so to speak. That being said, I'm not going to, like, if the correct answer isn't there because it's my mistake, which since I'm the only one making out the test, it has to be my mistake. I don't have any problem whatsoever giving you guys credit for your, pain and suffering or whatever. I'm not going to be like, well, you should have chosen J. I'm going to be like, okay, well, you should get compensation because you wasted your time because I'm a jackass. Let's circle back around to the problem at hand. How would we approach a problem like this? Okay. Yeah, source transformation. Exactly right. So somebody who isn't Ian, getting tired of hearing your voice, bud. How would we switch this guy to make it something that looks like either a practical voltage source or a practical current source? Okay, so how would I do that? Okay, so 12 volts divided by 3 ohms was 4 amps. All right. Somebody else, what comes next? All right, so what's 3 in parallel with 6, Joy? 2. What can I do next? Somebody new. Benjamin.
Go back to practical source of 4 and 2 ohms.
Okay, so go back to a practical voltage source. So since the arrow is pointed up, it's going to have positive sign on top. 4 times 2 is 8. So it's going to look like 8 volts in series. With 2 ohms. Jeffrey, you are staring at the board like you're paying attention. What do I do next? Yeah, so 2 in series with 7. Looks like 9. And boom, in just a few short steps, we have got a practical voltage source in series with our load resistance. So What is the answer to the first question? What value of RL will cause the remainder of the circuit to deliver maximum power? 9 ohms. Boom. When you only have one resistance left, that's the answer. All right. How do I answer part B? Literally just use the equation I gave you, right? P max is 1/4 VS squared over RS, 1/4 8 volts squared over 9 ohms. That's going to be 64 over 36 volts. I know that can be reduced, but I'm lazy. So that's a fantastic question. So if RL were 0, how much power would be delivered to the load? So if we're looking at the power absorbed by a resistor, and the resistor value is 0, the power absorbed by the resistor is 0. Yes. So what I'm asking is how much power is delivered to RL by the rest of the circuit. And specifically, I'm asking what is the maximum amount of power that can be delivered to that resistor RL, which means RL has to be non-zero and it has to be non-infinity, because if it's 0 ohms or infinity ohms, no power is delivered that way. So a short circuit absorbs no power, and an open circuit also absorbs no power, because in one case the voltage is 0 and the other current is 0.
So that 72 watts effectively be the power dissipated by the entire circuit as a whole, assuming RL is 0.
So if RL were 0, let's see, so that would be 864 over 9, right? B squared over R?
Yeah.
Yeah. So that would be the power that's being lost to the internal resistance of the voltage source. So not being delivered to some external load. And if the resistor, which is part of the voltage source, is absorbing 64 over 9, and the source is supplying 64 over 9, the practical source as a whole is delivering 0.